exam questions, which I am, I would ask about that. Yeah? That even though these are different bases, it's just a change of basis. I still have the same. Yeah? Okay. All right. And again, in fact, I have it on slide. Right? They all give the same formula. Okay. Now, obviously, polynomials are not the beginning and end of the story of like sort of basic, simple functions you could use to interpolate between data points. And in fact, I would say kind of the reasonable extension of polynomials, if you're following your high school algebra class, would be to move to rational functions, right? Which are just ratios of polynomials. So now I write f of x as a ratio, right? We have a polynomial with coefficients p and another polynomial with coefficients q. And I claim that you can still recover. So first of all, how many unknowns do I have? I have m plus n unknowns. Yeah, all the p's and all the q's. So I need m plus n. Oh shoot, m plus n plus 2. I did it again, right? Because we're starting counting at 0. So we have m plus n plus 2 unknowns. So we need at least that many data points. In fact, exactly that many data points if we're doing interpolation. And I claim that you can still find a unique polynomial or a unique rational function that goes through these points, if such a thing exists, using a linear system of equations. Right? And I use a cute trick to do that, where all I do is I just multiply both sides of this equation by the denominator here. Yeah? And what happens in that case? Well, obviously the q moves over to the left-hand side. Right? And remember the game we have to play is what's known and what's unknown. Right? What's unknown here are the p's and q's. So when I multiply both sides, right, and substitute x and y, right, this is just a linear relationship, this second equation here. Right? So I can solve it using linear methods. Of course, there's a slight issue here, which is that if I take all of the p's and all the q's and multiply them all by 7, for example, I get the same polynomial back out, right, or the same rational function back out. Right? Because I have 7 in the numerator and 7 in the denominator. They cancel. Right? So in fact, the linear system that I just wrote down for you has a null space, and you have to deal with that. Who knew? But that's not a big deal. It's very predictable what that null space is. Right? It's just scaling the p's and q's in parallel. Right? And so once you get rid of that, you can solve the system, and you can find rational interpolation. So a question, and in fact this is a question in my mind, because this is not a set of tools that I use very often in my research and my work, was, okay, well you see polynomial interpolation everywhere, and effectively the same machinery exists for rational interpolation, so why the heck don't people use rational functions? Rational functions are sort of better. They include polynomials, they have, they're more flexible, they can have asymptotes and so on. So what's the problem here? And the problem is that really scary, bad things can happen when you allow division by 0. And in fact, I cite, in the course notes, I cite a book that devotes almost an entire chapter to dealing with this problem. But we lifted an example from the very beginning of this chapter, where they say, and I'm going to follow along in my scribbles so that I don't mess up. But let's say that I'd like to find a rational function where both n and m equal 1. Yeah? So what is this f of x going to look like? It's going to be f of x equals p0 plus p1x divided by x and x, divided by q0 plus q1x. Yeah? Innocent enough. And I give you 3 data points, which is good. Yeah? So what's going to happen here? Well, so now let's plug in all of our different relationships. Right? So the first one we have x equals 0, y equals 1. Right? So in fact we'll get 1 times q0 equals p0. Yeah? And then for x equals 1, y equals 2, yeah, when we plug that in, we will get 2, right? That's the y times q0 plus q1, and that equals p0 plus p1. Right? I just put x equals 1, and I multiply both sides by the q part. Yeah. And finally, we have a third point, 2, 2. Yeah? And he's going to have 2 times q0 plus 2q1 equals p0 plus 2p1. Yeah? Now obviously I can scale all these guys up and down. So we need some additional constraint. But once we were willing to take care of that, in fact, I'm going to jump that step because I think you guys are all proficient high school algebra students, and we're going to write down a solution to this that's non-trivial, which is this. In fact, this is the only non-trivial solution up to scaling all these by constant. Q0 equals 0, and Q1 equals 1. This is the solution of this system of equations. Yeah, check this out. Well, what does this mean that f of x is equal to? Well, so all of the p0s are 0, right? And we have q1 is 2 and q1 is 1. So in fact, this says that f of x is equal to 2x divided by x. Yeah? We'd like to cancel those x's, but we can't quite. Right? So what happens? Well, when x is non-zero, in fact, this is the correct function to interpolate between these two data points. But when x is 0, f of x is actually undefined. You can't say that f of x is equal to 2. You can't do it. It's against the rules. Right? Because we're dividing by 0. Right? And in fact, if we were to cancel these x's, right, we get f of x equals 2, but that isn't the point that we want. Right? So in fact, algebra has tricked us again, and by multiplying both sides by this denominator, we actually cheated a little bit, because we discounted the divide by 0 case, and it turns out that case makes all the difference. Yeah? And in fact, you can show that these three data points have no interpolating rational function that has this form. It just doesn't. You know? So anyway, all of this is just to say that you can make a very innocent looking extension of machinery that is very well behaved, and what comes out is a total monster. And in fact, the resolution to this problem is completely unsatisfying. What these people do is they'll write these algorithms that just slowly increment n and m until they find a rational function that interpolates these data points. But somehow, that's very heuristic, right? It's unclear what your choice of n and m should be, for example, relative to one another. Yeah? If you like that, I cite a book that does this stuff. It's kind of fun to read. You can find it for free on the internet, although I don't think it's supposed to. Anyway, right. All of our basis functions so far have been kind of polynomial, rational looking, but that's by no means the only thing we could do. And in fact, a very, very, very well-known choice of basis functions is to do all of the cosines of kx and sines of kx, for k being just any integer. Yeah? This basis has a name. It's the Fourier Basis. And it just looks like a bunch of oscillatory functions that are squeezed into smaller and smaller spaces. And in fact, if you take k off to infinity, this is guaranteed to approximate any function on the interval 0, 1. Fun fact. And right, so the field of Fourier analysis is all about, one way to think about it is actually about interpolation, right? And so if you take CS 148 and you learn about sampling, right? Basically the problem when you undersample a function, like when these points are so far apart that you really can't make much sense of what goes on in between, the problem is all about interpolation and the fact that your basis functions really don't line up with the sample points that you have. Yeah? So anyway, maybe we'll do the homework, maybe we won't. I don't know. I haven't decided yet. But that's all we'll mention about Fourier in class. So anyway, if we return to the polynomials, or in fact these cosines and sines that I just mentioned, or in fact these rational functions, they all have kind of similar problems, which is that if I make a local change, like I take one of my yi's and I kind of scoot them up or down, I can have a global change in the polynomial I get out. Does that make sense? Like, for example, kind of the obvious one, right? If I'm trying to find a parabola that goes through 3 points, right? Yeah, and I have 3 data points, 1, 2, and then I think of the third one as one of these points along this line. Obviously, my function is globally affected, right? If I have a parabola through these points, it will go through that. If I have a parabola through these 3 points, it would go like that. Bad aim. Yeah? But here's the thing. No matter how far off to the right I go, this choice of this one data point has affected the value of my function. Pretty drastically, in fact. Yeah? In fact, if I just take 2 points very close to this line, And between these, right, if I go out far enough in this direction, I can have globally, humongously different results between positive and negative numbers. Right? Now obviously this example is kind of stupid, right? We only have 3 points, and so it's sort of reasonable that it would affect the global behavior. But even if I added a bunch more points to my polynomial, right? So I'm fitting some polynomial that goes through all this stuff, right? Changing any one of these points will have a global effect on the behavior of your function. And that's like, that's bad news, right? Because if I have like a very densely sampled function, right? Somehow, if I like take this one point and I jiggle him up and down a little bit, I expect his effect on the interpolated function to be kind of limited to just the neighborhood around him. But that doesn't happen for polynomials. Yeah? So I would say a useful vocabulary word when we're talking about these sorts of things, that polynomials do not have compact support. Okay? So how many of us have used the phrase compact support before? In our everyday lives? No? Yeah. So a function with compact support is pretty easy. It says that there's some number c, so that outside of the range from minus c to c, g of x is just equal to 0. Right? So like in other words, there's some little set on the real numbers for which this thing has non-zero values, and everywhere else it is exactly 0. Do any polynomials other than 0 have compact support? No. Right? They all go off to infinity and have these big numbers that are going crazy as I go far away. Right? And so what happens when I write functions in the polynomial basis, right, is that the influence of this one data point has to do with everybody else along the entire number line, because the functions that touch this data point are the same as the functions that touch this data point, that data point, and so on. Right? So this is a big issue when you're doing interpolation, that our basis functions have infinite support. They go on forever. By the way, it's easy to define a function with compact support on like R2, right, where you just say there's some compact blob, and inside of that blob your function has non-zero values and everywhere else that it's 0. And when I say 0, I don't mean like close to 0, I mean 0. Yeah? So you can see how then two functions with complementary support, for example, right, would mean that they're non-zero in different places, and they just don't affect each other at all, right? They can happily move up and down without affecting any values they have in common. Yeah? So a common next step would be, okay, let's try and construct basis functions that have compact support, right? Because then sort of the number of basis functions that touch any given data point is a lot smaller. Right? So coming up with C-infinity functions with compact support is a fun trivia game, but in fact usually we don't bother and we just say that they're differentiable to some degree, although such a thing does exist. And we come up with these things called piecewise polynomials. And I'm now realizing there are far too many words on this slide for a very simple concept. So I will draw a picture. So the idea of a piecewise polynomial is exactly that I'm going to divide the real numbers into a bunch of little segments, and then in each segment I'm going to have a different little polynomial piece, and they're all going to fit together. Yeah? So this is the simplest piecewise polynomial function would be one that is piecewise constant. And what does that mean? That means that in each interval, my function just takes a single value. Yeah? So piecewise constant functions are super easy to deal with. Here's one. I'm not even all that concerned with like who owns this point. I don't do whatever. Although you should be when you implement these things. Yeah? This is a piecewise constant function. He's certainly a piecewise polynomial because if I take my domain and I just partition him into these little pieces, right? In each of these pieces, this thing is just a constant function. Right? Constants are certainly polynomial. Cool. So what's a piecewise linear function? Well, I think you can probably guess. Okay, so this is usually we write PC for piecewise constant, by the way. You can guess what I'm about to write here. This is a PL function. And by the way, in the theory of finite elements, these two letters show up over and over and over and over and over again. And Gavin should be used to this because he took 468. And yeah, so a piecewise linear function is one that sort of has these little knots and then just straight lines in between them. By the way, the knots don't have to be equally spaced. Cool? Super simple. Yeah, piecewise quadratic function is just one that has little parabolas. And so what is our pattern here? Well, notice that, so we can call these points here, right, where you switch from one polynomial to the other, we can call those joints or knots. Yeah? And at the knots of these piecewise functions, For example, if you're piecewise constant, then you expect there to be a discontinuity. If you're piecewise linear, you now are continuous, but you have a slope discontinuity, right? So this function is C0, but not C1. If you're piecewise if you're piecewise quadratic, you made little parabolas. You can in fact, I can attempt to draw a picture of this. I used to TA this class. So one thing you could do would be you have a bunch of data points, and now you can also draw little slopes on them. Right? And you can find a parabola that goes through each of these segments, that goes through these points and has the proper slope, so that they match up like that, and so on. Right? By the way, these piecewise quadratic things are still only C2, right? Or C1. They have continuous first derivatives, but their second derivatives change in each of the joints. And so if you're interested in HCI and these sort of human aspects of these graphic stuff, an interesting question is, why is your eye really good at detecting these sharp corners, but bad at detecting, for example, curvature discontinuities or third order discontinuities and so on? And how many terms do you need? This is a very important question if you're designing Photoshop, right? And then in Photoshop, when you use these tools where you draw little, you put a bunch of points down and now you want a little curve that goes through them because you're drawing something. Basically behind the scenes, that's just a piecewise polynomial function. There is a very large theory that involves piecewise polynomials and understanding how to make the tangents line up and how to control them and so on. And that theory is covered in detail in CS 348a, which I encourage you all to. But this class being what it is, we're going to have to move on. No? But just like before, right? Now, if we're taking the CS 205a standpoint, right, then we don't care about de Castel-Jogues algorithm and subdivision curves and all these fun things. But instead, all we care about is that we're trying to interpolate a function, and we're doing so in a basis. And we still have a basis for piecewise polynomial functions. They just don't look like the basis we're used to. Right? So usually we think of our basis functions so far as being like, x cubed minus x squared plus whatever, or like some polynomial or transcendental thing I could just write down. Right? But a piecewise function now is going to need one of these funky bracketed definitions, where you say like, well, when x is in this interval, for example, the interval around xi, then take 1, and when it's in the interval elsewhere, then take 0. Right? So this would be, so the idea of the basis functions that you might use would be that maybe you have your data points are x1, x2, x3, x4, right? They're like saying the midpoints of all these intervals. Right? So my basis function is the guy that is 1 on this interval and then 0 elsewhere. Yeah. And obviously I can linearly combine these in easy ways to get the interpolation. Cool. Similarly for piecewise linear functions, the form is like kind of funky to write down, but it's very simple. We call this the hat basis. Yeah. So the idea is that let's say that I have, and notice that I'm tailoring my basis to the xi inputs that I have. Right. So in particular, I have a bunch of x1, x2, x3, and usually we like our basis to be 1 on one of our data points and 0 everywhere else. Yeah, so usually our hat basis looks like this. So let's say that so here's x1, let's say I'm at x2, then my basis function is going to increase from 0 to 1, yeah, as I go from x1 to x2, and then from x2 to x3, we're just going to linearly decrease, right? And so this still has that nice convenient property that we like from the Lagrange polynomials, right? That interpolating this function is just summing up these different hat functions times the yi values upstairs, right? Because that's going to just scale the height of this peak. And since everybody else is 0 at this point, we know that we're going to get the right thing. And in between, we're going to get lines. It's just some bunch of them. Yeah? And this is called a hat function, right? Because it looks like a hat, sort of. Right, and we're going to come back to this again later in this lecture, and actually again when we talk about partial differential equations, because the finite element method makes very strong use of exactly these functions, where we say sort of we can't expect to solve a PDE at every point in a domain, so we're going to have to do some interpolation, and the hat functions actually are pretty reasonable for a lot of simple problems. Right. One observation, which is again, you'll notice today's lecture is a little bit of a sketch of a lot of different ideas rather than humongous detail, because each of these is a very big iceberg. One thing that's very tempting when you deal with piecewise polynomials is to take the degree as high as you can possibly deal with. Right? And obviously our processors now are very fast. We can do we can evaluate polynomials certainly of more than degree 3. And so an interesting question is sort of, well, what the heck? Why not do that? Why not have like a piecewise quintic function, right? And then I can make sure that my functions are at least C4, right? That is that up to the 4th derivative, they're all of those are continuous. But it turns out that for a number of applications, this is a bad decision. And the reason is that discontinuities happen in real life, right? So if I write a function in this piecewise C4 way and enforce that the derivatives all match at the joints, right? Kind of the typical setup, then what you're really saying is that all functions you expect to see in everyday life should be 4 times differentiable. Yeah? This is actually a discovery that people made, I think, around 60 years ago. They were doing fluid simulation, right? The real reason that everybody seems to take these kinds of classes, right? They wanted to simulate splashes, and in particular, if I want to simulate an airplane flying around, right, then we know that if airplanes go fast enough, they have this shock wave, right? This sonic boom thing that happens behind them, right? In fact, apparently, is that illegal, or I don't know how this goes. Right? That Concorde jet created some issues with this. But that aside, if I wanted to simulate this phenomenon, right, I have this jet that goes fast enough and I get this shock, that is a discontinuity, I believe, in pressure, right? If I try to simulate a shock wave using 4th order continuous objects, I will fail. My simulation will not work. And the reason is that the set of functions that I'm dealing with simply doesn't know how to talk to discontinuities, right? And so when I do it, what's going to end up happening is you'll see these really strange phenomena, right? This is called the Gibbs phenomenon, when I try to approximate, let's say I want to approximate this step function, right? Well, if I try and make this thing smoother, oftentimes what will happen is I'll get like a bunch of really crazy wiggling like that. Right? You've probably seen this before. And that's because I'm making more assumptions about my function than I should. And somehow when I project that into the space of functions I know how to deal with, I get something really strange. Right? In fact, then, if I have one of these phenomena and I'm simulating a shock wave, well, now I have all this weird wave material that's happening here, and that can start propagating in funny ways to the rest of my domain. So this can have really disastrous effects. So anyway, all this is to say that you should sort of use exactly what you want and what you need and no more. Right? If you can't think of a reason why you need your function to be like 400 times differentiable, then don't use 400 times differentiable functions. Yeah? Okay. All right, so we started today, as we are apt to do, by considering how to interpolate functions in a single variable, but oftentimes we are not so lucky and we have more than one input. Still one output, right? We're still going to just output one number at a time. Obviously, dealing with functions from Rn to Rm is as simple as doing this one output at a time. Yeah? So, so now our inputs are going to be a bunch of pairs x, y, but now the x is going to be a vector in Rn, and it wants to match the y. Unfortunately, this is actually a considerably harder problem. It's, I think your textbook doesn't even touch this, but I thought we'd mention a couple strategies that are sort of reasonable, because I do think that this shows up very often in life, right? Not all functions are one variable. In particular, the simplest possible thing we could do is, let's say that I'm walking around Rn. The plane is a good version of Rn. That's R2. Yeah? And I want to find a value f of x for just some arbitrary x, given sort of this scattering of values elsewhere. Right? One thing I could do would be to just look in this whole cloud of x's that I do have, and just find the closest one to where I'm standing, and just take his value y. Yeah? So this will make a piecewise constant function. We're going to see what this looks like in just a moment. And basically what's going to happen, in fact, well, I'll show you right now, is that the function, there's going to be each point, right? So each of these black dots here is a different data point xi, right? So what's going to happen is when I interpolate a function of the rest of the plane, right? You can think of like this black point here owns some little piece of the plane for which all those all the points on that piece of the plane are closer to this black dot than to any of the other black dots. Yeah? So all of those points in that brown region are all going to take the value y associated with that one black dot, right? And that cell is called the Voronoi cell of that dot. So the Voronoi cell of a point is nothing more than the locus of points that are all closer to that one guy than any of the other ones in your data set. And so when you do nearest neighbor interpolation, which is very simple, right? All I do is I iterate all of my data points and just find the closest guy, yeah? Then effectively what I'm doing is this, I'm interpolating based on Voronoi cell. And the Voronoi cells have lots of beautiful properties. Today we're going to be referencing lots of other Stanford courses, many of which are taught by folks in my group. And if you take CS 268, I believe, you will understand Voronoi cells in more detail than you will care to. And the basic idea is the really interesting observation that a man named Bilinear made is that if you look at the connectivity of the Voronoi cells, for example, like this brown guy is adjacent to this blue guy, right? That induces a graph on the black points, right? So every time that the brown cell is adjacent to some other cell, I'm going to put an edge between the corresponding points. That is a very, very important graph. It is called the Delaunay triangulation of these points. By the way, I use the word triangulation. It's not clear that graph should even be a set of triangles, but in fact it is. And it's a very well-behaved set of triangles, in fact. So CS268 is really fun. You get to like play with all these high school geometry facts about like circles and things. And it all boils down to Voronoi cells and Delaunay. But anyway, if you do nearest neighbor interpolation, you don't have to worry about any of that. To compute the closest point, you can just look at all the points and find the one with the smallest distance. Or use something fancy like a KD tree. And in fact, you'll get this nice interpolation here. And these Voronoi cells have all kinds of cool properties. They're convex, they're polygons, and so on. Now, that's by no means the only strategy. And in fact, oftentimes we'd like functions to be at least continuous, right? Obviously, if I use nearest neighbor along the edges of Voronoi cells, I have discontinuity. Yeah? And unfortunately, getting a continuous interpolation of a function on anything other than real numbers can be a really big challenge and kind of a headache. So one strategy that I chose to develop in a little bit of depth is this idea of barycentric interpolation, which is very popular in computer graphics. Now, let's say that I have n plus 1 points in Rn. Right? So in particular, let's say that I'm on the plane, then I have 3 points, right? The plane is R2. And we're assuming they're in general position, meaning that like they're all kind of scattered about. They don't all lie on the same line or something degenerate like that. Right? And now I'd like to find, and I have this is, x1, x2, x3, and I have f of x1, f of x2, and f of x3, right? And now let's say I'm standing at some other point. My question is, what should be f of this point? Yep, same question we've been answering all day today. One thing I could do is say geometrically, this point is some weighted average of these 3 guys, right? So what I can do is compute the weights of that weighted average, and then use those to average the f values. That's called barycentric interpolation. So to be more specific about that, what I would do is I'd find a set of weights A, right? And I would say that now I'm standing at some x on the plane, and I'm going to express him as a weighted sum of all the xi's that I have, right? And since I want it to be a weighted average, I've got to have my weight sum up to 1. Yeah? So when I do this, it's called barycentric interpolation. It has a beautiful interpretation on the plane. In particular, let's draw this a little bit bigger. Let's say that I'm inside of the triangle, and I want to interpolate f at this point here. Then one thing I could do would be to draw lines from this point to the 3 vertices, and look at the areas, A1, A2, and A3. So we're going to call this x1, this x2, and this x3. Right? And it turns out that the weights in the weighted average are proportional to the areas opposite the vertices. Right? This makes some sense, right? For example, if this point goes to x3, then a3 is going to dominate the whole triangle. You know? And in fact, you can, it's not worth checking today, but that's the nice sort of geometric version of what barycentric interpolation is doing. But there's a big drawback. There always is, right? In particular, if I want to function on the plane, then how many data points can I have? I just told you, somebody. 3. I can have 3 data points, yeah? At the vertices of this triangle. Hopefully you guys are following me. If you're not, you should stop me. Yeah? So if I want to interpolate a function of which I only have 3 data points, the entire plane, I'm good. But that's not a very realistic case. Yeah? So an interesting question is, well, what do you do when you have more data points? What do you say we need at least 3? Below 3 and you're kind of in trouble. Oh, yeah, and there's our interpolation. Well, one really cool strategy is to say, okay, well what happens? Remember we have this linear system of equations to find this A vector on the slide here, right? This is the thing that's expressing our new input x as a weighted sum of the points we've seen. Well, if we have more points, then that system for A becomes underdetermined. Right? So a really interesting research problem is if I have like 20 points on the plane, and now I'm standing at some point, and I'd like to express them as a linear combination of those 20 points, I have a lot of options. Right? And so one thing you could do is try and write down additional properties of A that would be convenient. For example, that A is smooth, that A is sort of localized to just the points nearby, and so on. Right? And each of those gives you a different system of barycentric coordinates for these 20 points, and can be used for interpolation problems. So here, this person, actually one of my colleagues, she interpolated the texture coordinates of this bird, right? So he's originally in this polygon here, and then they move the vertices of the polygon, and that effectively is warping the bird underneath. And you can see that the deformation that they get is nice and smooth, and sort of localized to the different body parts of the bird. Yeah? So you can read up on this online for some kind of fun approaches to this. Another idea would be that I take the plane and I say, okay, so barycentric interpolation only knows how to deal with triangles. Yeah? So one thing I can do is take the whole plane and just divide it into a bunch of triangles. Right? In fact, the Delaunay triangulation I mentioned would be a good option if you didn't have one ahead of time. Right? And say, okay, well in the interior of any given triangle, I'm just going to use the barycentric interpolation induced by his 3 vertices. Yeah? If I do that, then in fact, effectively what I'm doing is writing my function in a basis of half functions. But now the half functions are barycentric hats that are centered at the vertices of this triangulation of the plane. So again, this is one of these things where the details are kind of annoying to work out, but the picture is actually very simple, where you have just like a different basis function living at each vertex, and it's nicely localized and so on. Right? This is a very common approach in computational geometry. Cool. So we started today by mentioning that when you do image processing, you need a method for interpolation. Right? And in fact, a very special case of interpolation is when you have a grid of points where you know values. For example, on an image, right, you assume that all of your pixel colors are sitting on that image grid. Right? This is different from what I just showed you, where you have a triangulation and you know values on the vertices of that triangulation. Right? That's somehow more complicated because, well, you've got to find the triangles for one thing. You know? So if you'd like to do interpolation on a grid, that's a very classical problem. There are many approaches to this, and you should be careful because oftentimes they are specialized to grid in a funny anisotropic way. Meaning that if I took my grid and I rotated it, I would get kind of a different interpolation, which is a little bit of a weird property. But that aside, the most common one, and the vocabulary word that you should get out of this little piece of our lecture is this idea of, for example, bilinear interpolation, which is very simple, right? So the idea here is now if I have a square of values, right, then I have 4 numbers, A, B, C, and D, right? And then what I'm going to do if I want to find this point, right, is I could, for example, draw a horizontal line, right, and use these 2 numbers this way to interpolate. You know, we'll call this